Hey everyone, what's going on? Hopefully you're having a good day, night, whatever time of the day it is for you that you're checking this video out. I wanted to make a video for you on one of the extension lessons for this week. As I mentioned before in my email and in our conversations in the Google Meet, there's going to be an extension lesson offered each week. That extension lesson is not required to get your credit for the semester. However, it is something that you're going to want to at least take a look at if you have more time because the assignments don't take that long. You have some downtime on your hands, you're bored. But especially if you're planning on taking pre-calculus next year, these are some prerequisite skills that will be helpful coming in because we're going to miss out. This is stuff that we would have learned this year, but since we're not technically teaching any new content online that's required, I'm going to teach new content as an extension. Things that you're going to want to know whether you're moving on to maybe pre-algebra in college or pre-calculus next year, whatever grade level you're in, whatever math you're going to take next year. These are some good prerequisite skills. The first one that we're going to talk about today are special right triangles. So there are two special right triangles here. And bear with me as I go through this. For some reason on Google Meet, my document camera on my screen shows up backwards. It should show up normal for you, but as I'm writing and adjusting and trying to make sure it's all on the screen, it might take me a minute there to get that correct. So anyways, we're talking about special right triangles today. The first special right triangle we have is a 45, 45, 90-degree triangle. There are two special right triangles that we're classifying by their angle measures. So right triangle, obviously meaning it has a right angle, and two 45-degree angles. What makes this a special triangle is those two 45-degree angles. Because if the angle measures are the same, then the side lengths are also the same. And there's a relationship that this triangle has. That relationship is however long this side is here, obviously it is the same side length here. Um, Through Pythagorean theorem, through distance formula, through other things that we can derive, we're not going to derive why this is true, but I'm letting you know that this is a property of a special right triangle, of a 45, 45, 90 triangle in particular, is that if you know that these are both, I called them L right now. So if these are both side lengths L, then you know the hypotenuse of the right triangle is L times the square root of 2. That's a special property of special right of this 45, 45, 90-degree triangle. So for example, with numbers, if I had a 45, 45, 90 triangle, I can see that it's labeled that clearly. Then if I know that this is 3, I also know that this is 3 because, they're the same side length. They're both across from the 45. Then I know that the hypotenuse is 3 times the square root of 2. It is always whatever these side lengths are times the square root of 2. That's always the case. So that's the rule. We're going to get some practice and some examples on those in just a minute of how to solve for missing sides. But that is the rule for the 45, 45, 90 triangle. So you may want to write that down somewhere. Keep that filed away on a notebook, maybe. We're going to refer back to that in just a minute. The other special right triangle is what we call a 30, 60, 90 triangle. So the angle measures, again, it's a right triangle, so it's got one 90-degree angle. And the other angles are 30 and 60. Just like the 45, 45, 90, this has special angle leg relationships here. And so here's the general rule. So for a 30, 60, 90, the first thing you want to be able to do is identify which one is the 30-degree angle and which side matches with that. We have three angles, 30, 60, 90. 30 is the smallest angle measure. So it's going to match. It's always going to be across from the smallest side length. So smallest angle and the smallest angle is across from the smallest side. And that's always going to be the case. So the big thing is and let me move that so you can see it. So the biggest thing is to be able to identify that in a given problem. So we're going to practice that in our examples today as well. Are you able to identify the smallest angle measure and the smallest side length? And they go together there. The special relationship in a 30, 60, 90 triangle is that if you know the small side length, if you have that, or if you have one of the others, we'll work on working backwards. But if I know that that small side length is, let's say, L, then I know that the other side, right, sides or the legs of the triangle are the two that form that right angle. So the other leg, the big one across from the 60 degree, the bigger side, is that same number, L, times the square root of 3. And the hypotenuse in a 30, 60, 90 triangle is that L times 2. So whatever that L, whatever that length is for that shortest side, times 2 is going to be the length of the hypotenuse. So an example with some numbers here. So if I know that, again, identifying, here's my 30 degree, here's the short, and the short side, short angle, short side, small angle. Those match together. So this is the 30. This is that L, if you will. So this is my kind of starting number there. Then I know the other leg, the 60 degree leg, the one across from 60 degrees, is going to be that same number times the square root of 3. If we look back at our rule, it is L root 3. So I take my L, 3 times root 3. And I'm just going to leave it as that. We want exact answers. Sometimes Khan Academy might ask you to put it in closest decimal form. A lot of times we want to do exact answers. The other thing, the hypotenuse, is the L times 2. So 3 times 2 gives us 6. And so that's how we figure out the side length there. So let's take a look at a couple examples. A few things is, let me just jot down a few notes. So you need to be able to identify which special right triangle, identify which special right triangle you're dealing with, and then also being able to identify what info do you have and what do you need. And you can't see some of that. Let me move that over. So what info do you have? What info do you need? Again, what I mean by this is what info do we have? Do we have the hypotenuse, or do we have a leg? Do we have the short leg? Do we have the long leg? So being able to identify what piece of that triangle you are actually given is going to be key there. So let's take a look. I'm going to draw up a couple examples for us to work through. So the first one I'm going to do, going to give us a rough sketch of these triangles here. So we've got this. So we're going to solve for 2 variables each time we do a problem here. Call this one X and one Y. Okay, so first thing is, which triangle do we have? And I should be able to recognize that because my 2 angle measures are the same, they have the same marks, that means that these have to be, right, triangle sum theorem. There's 180 degrees, 90 of it's here. So 180 minus 90 is 90. Divided by 2 has to be 45. Because these angles are the same, this has to be 45 degrees, and this has to be 45 degrees. If they're the same, it's automatically going to be a 45, 45, 90 triangle. And if you remember that, then you could very easily just sketch the rule again. 45, 45, 90 triangle, L, L, L root 2. Okay, and so I'm just going to write the rule off to the side, and that's going to help us figure out what X and Y are very easily. If I know that X and Y actually have to be the same thing, because it's the 45, 45, 90, I really just need to find one, and I can find the other one. I know that if I knew what this number was, right, if I knew what this number L was, I multiply it by the square root of 2. This is L root 2. So I have 6 root 2. This really is your L right here, right? 6 is really just the L. So that means that X will equal 6 and Y will equal 6. And that's it. That's it for our first example. Second example, pretty quick, same idea here. Let's see. Okay, second example. Again, can we identify the triangle that we're dealing with? So is it a 45, 45, 90 or a 30, 60, 90? Obviously, it is a 30, 60, 90. There's a 90 degree here and a 30 degree here. The last one has to be 60 degrees. So we're now dealing with a 30, 60, 90. Again, once you know which triangle it is, if you go ahead and just write down the rule real quickly, what we said before on the previous page was that if this is the 30 degree, then this is the L. Remember that those kind of go together. So the small side goes always with L, like that base letter. Then I know the hypotenuse is 2 times L. And I know the other leg on the other side of the 90-degree angle is that L times the square root of 3. That's the rule that we discussed on the previous page. So again, based on this information, if I know that this is across from the 30-degree angle, right? We've got 30 degrees. We've got the number 8 here. They're across from each other. I know that that's basically the same part as I have here. So that's my L. So I know that if this is my L, then I know that Y has to be 2 times L. So 2 times 8 would give me 16. And X is L times square root of 3. If this is my L, then this is 8 root 3. So again, this is really the L from the other diagram. Identify what kind of triangle you have, identify what you need to find, apply the rule, and solve. Really just writing down the number. Nothing terribly challenging. Let's take a look at another example here. We've got a 45, 45, 90 triangle. I'm going to go ahead and label it this time. I'm going to call this, let's go 5 root 2 and 1. A little bit more challenging here because, again, we know we're dealing with a 45, 45, 90. So let me write that down, 45, 45, 90. We know we're dealing with that. We know the general rule for 45, 45, 90. L root 2. But notice the difference here. Notice the difference now, right? This L, the side length, is what we have over here. We know the side length. So I know that those are matching here. I know that's across from one of the 45 degrees. So I know that these two have to be the same, right? 45, 45, 90. So I can figure out X is 5 root 2. But Y is a little bit trickier because in order to go from here to here, I multiply by root 2. But there's already a root 2 in my problem. So let's write out what that looks like. So this would be, it equals whatever this number is, which we have circled over here, 5 times the square root of 2. So that's what this says right here in the circle, times another square root of 2. Times another square root of 2. So this is where understanding your radical properties comes in. So 5 root 2 and 5 times the square root of 2 are the same thing. So I'm going to rewrite it like this. And so since this is times and this is times, I can do them in kind of any order I want. So I'm going to go ahead and I'm going to multiply square root of 2 times the square root of 2. And what happens when we do this is we're really multiplying that inside of one radical together. This is really like 2 times 2, which is 5 times the square root of 4. Okay? And then the square root of 4, we should know, is 2. So we get 5 times 2. And we simplify that to get a final answer of 10. So Y is really equal to 10 in this case. This is the rules here. When you multiply two radicals together that have the same number in them, basically what's happening is you're squaring that number and then taking the square root. So you're going to get, when you have root 2 times root 2, you're going to get 2. If I had root 3 times root 3, the answer to this, if you put it in a calculator, is 3. If I had root 5 times root 5, the answer is 5. If I had root x times root x, the answer is, it's a little bit off your screen there, is x. So this is just a little side note here, how radicals work when you multiply them. Okay. So when you multiply radicals that have the same number inside of them, then you end up with just that value on the outside. So when I do root 2 times root 2, I really get 5 times 2, which is 10. All right. Let's take a look at another example. We'll go back to a 30, 60, 90 triangle. And let's do let's start with this one. And why? Okay, so again, identifying it's a 30, 60, 90. I'm going to start there and I'm going to rewrite the rules. I know it seems redundant, and if you already have them written on a separate sheet of paper that you can look back at, it's much nicer, so you don't have to constantly be rewriting the rule down. But it is nice to have that, and it's nice to, even if I just keep rewriting it and practice it over and over again, then it starts to help stick in my head. So I know that across from the 30 is the L, 2L, and L root 3. So the reason I drew this problem, our example, the way I did is because I wanted to make sure that we're paying close attention to where the numbers are located. So remember that L is always across from the 30 degrees. So in this diagram, while it might not be drawn to scale, we have to identify, okay, here's the 30-degree angle. So what's across from it is that what we call L, right? That's our L. And so that's what's across from our 30 degrees, which we don't actually know in this case. That's a variable. What I do know is across from the 60 degree, right, is L root 3. So across from the 60-degree angle, L times root 3. So if this is L times root 3, now we know what our L is. Our L is this number 3 right here. So I know that X, which is just that number, whatever is in front of the square root of 3, okay, so that would be 3. And then I know that if I know this number, L, if I know this number that's across from the 30, then I know the number across from the 90 is double that. So I know that 3 times 2 is 6. So that triangle for X and Y would be X is 3, Y is 6. All right. So maybe we'll take a look at one more example here. And of course, you can always pause the video, rewind it, go back and look at an example if there's something you need to know. Come see me in office hours if you have a question about any of these examples. I'll be happy to answer them, especially people that are taking the time to work on this. So I'm going to look at another 30, 60, 90. So before I even put the numbers, I'm going to draw our general triangle, 30, 60, 90. Make sure I remember the rules. 30, L, 60, L root 3, and 2L. All right. And so for our example, what I'm going to do here is I'm going to put the 12 here. I'm going to put X here and Y here. So here's our last example. A little bit tricky, kind of like that last 45, 45, 90 example where I'm throwing a little wrinkle in here because normally across from the 60 degree, we see like a root 3, right? Like it's across from 60, L root 3. In our last example, across from 60, 3 root 3. It made it nice and easy. This one, not quite the same. So this one's a little bit different. This involves a little bit more algebra to be able to simplify correctly because we want our answers in exact form. We don't want decimals. So we're not just putting them into a calculator. So again, 30 is across from the short side. We know 60 is across from the root 3 side. The problem is it's not actually there. But what we can do is we can write an equation to help us solve for X here. So what we know is that if I take this value that's across from 30 degrees, if I take this value, which in our case is X, if I take X and I multiply it by the square root of 3, if I take L and I multiply it by the square root of 3, I'm going to get this answer over here, right? I'm going to get whatever is across from the 60. So if I take what's across from the 30, which in this case is X, I multiply it by the square root of 3, I'm going to get whatever's across from the 60 degree, which in this case is 12. This is an easy way to set this problem up to understand what's happening mathematically. I could have done the very same thing in any of these other problems. You take whatever's across from the 30, multiply it by the square root of 3, and that gets you what's across from 60 degrees. All right. So now I want to solve this for x. So I'm going to divide by the square root of 3. And here's where we run into an issue. For those of you algebra savvy people at home, and maybe those of us that aren't quite sure, we need to remember what happens when we divide by a radical. We cannot leave it there. Yes, this will go away, and we're left with x equals 12 over root 3. But this is not called or not considered a simplified solution. We need to get rid of that radical in the denominator. Well, luckily, we already talked about how to deal with radicals. How do I make a radical go away? If I take a look back here, I can multiply by itself. Right? If I take the square root of 3 and I multiply it by itself, the whole radical symbol goes away. So we're going to use that same principle here, that same idea, but instead of just by the square root of 3, I have to multiply by a number that doesn't change my problem, which the only thing that in math that does that is the number 1. So I'm going to multiply by the number 1, but I'm going to make it look different by saying the square root of 3 over the square root of 3. If you put this in your calculator, root 3 over root 3, you will get 1, right? Same thing on top, and the bottom equals 1. So I'm really multiplying by 1, and I multiply straight across. So in the numerator, I'm going to get 12 times the square root of 3. I can't really do any math there because the 12 is not in a square root. 3 can't come out. There's nothing special about it. In the denominator, square root of 3 times square root of 3, what we just talked about, is 3. So now what I did is I took the radical that was in the denominator and I multiplied by 1. Now there's no radical in my denominator. That is simplified. This isn't completely simplified, but that is more simplified, more correct than what we have over here because we do not have a radical in the denominator. The reason we don't like that is a few reasons that we kind of talk about later on, but imaginary numbers, other possible solutions, things that we don't want to happen that may end up occurring in a specific problem. We just need to simplify one more. We know that 12 and 3 are divisible, so I can divide 12 by 3, which is really 4 times the square root of 3. So that may have been a little bit more work to solve for x in this problem because there's a little bit more algebra involved depending on the way the problem is set up. You can get some very easily set up problems, easily solvable problems. You may get some problems that are a little bit more difficult, a little bit more algebra in order to solve. Once I know this number, right now I know that this is 4 root 3. So this is 4 times the square root of 3. Now, to go from across from the 30 degree to the hypotenuse, I just double that. So I take my L, I multiply it by 2, I get my hypotenuse. I take my 4 root 3, I times it by 2, and I get my Y. So I take my 4 root 3 times 2, and I get 8 root 3. So if I go ahead and fill that in up here, my Y value here would be 8 root 3. Definitely a little bit more tricky than some of our easier examples, and you will get a mix of both. You'll get a mix of both types of problems, and it would be a lot easier if you used your calculator to get decimals. My suggestion, use a calculator and decimals to check your work. See if you're getting the right answers or see what the answer should be close to. And then maybe you can work your way through it after that. But our final solution should be in radical form if there is a radical in the problem. So we should always be looking for that. And those are special right triangles. So we've got the 30, 60, 90, the 45, 45, 90. I'm going to go back to that front page of examples real quickly here. And just kind of give you one more view of that. Let me see if I can zoom out. document camera does not like to zoom very quickly. That's our first examples. There we go. That's what I'm looking for. All right. So our special right triangles, our general rules, and those are what you will be working on for this week's extension lessons. For Thursday's office hours, you're more than welcome to ask questions about these types of problems. I'm going to be posting some practice. I'm going to give you some answers with the practice as well, just to help you check your solutions along the way. And if you are not sure how an answer is being reached, it's not going to have the work on it, but it will have the solutions. So if you're not sure how that solution is coming about, feel free to stop in Thursday, 8 o'clock at night for the open office hours, or feel free to email me, send me a message if we need to set up a Google Meet just to talk about some of these problems. I'll be more than happy to do so. So thank you for watching the special right triangles video, and hopefully this makes a lot more sense and you are able to complete those problems. And I will see you next time.